Okay, so difference between load and store. What's that one? Go ahead.
Load loads from memory onto a register. Store pulls from the register and stores it into memory.
Okay, so we load from mem into register, and we store from register into mem, right? All right, what about immediate values?
Integer literals.
Integer literals. So we were able to load into a register an immediate value. Okay, similarly, we could store into memory an immediate value. All right, so these are int literals. You can say hard-coded int value, something like that. All right, questions about that stuff? So should have been pretty easy, I would hope. All right, so now, what class is this? This one.
Oh, it's 250.
I can barely see what's on my screen anymore these days, so it's like a major issue up here. You think I blow the font up so you can see it. All right. So let's see. I had you read up. We're going to look at sign numbers today. I had you read. What have you done? All the way through 2.3?
Yeah.
Let me make sure there's nothing at the bottom of that I want to babble about for a few. Remind me, we figured it out 2 classes ago, I think. How big is a word in this language?
32
bits.
32 bits. So a half is 16. A double word is 64. Okay. That's kind of the vocabulary we're working with. There's store instructions. Okay. So let's talk about signed numbers now. And I referenced this before, and I'm going to spend most of the time on the slides here, and then we'll see how the book talks about it. But whatever I say is the right way. So if the book disagrees with me, it's wrong. It's probably the right way. All right, so storing negative numbers. So we have kind of 3 approaches here. I'll just kind of put out the 3 approaches initially, then we'll look at these guys in passing. So one kind is called sign and magnitude. Okay, another one is called one's complement. Another one is called two's complement. All right, so now punchline here is that two's complements are a winner. But now today we're going to talk about why. Why do we have 3 different ways that it could be done? And we'll talk about what the weakness of these is. And this is actually going to relate back to, I'm going to call it a tiny white lie from previous classes when we talked about, remember this slide from probably 200 maybe, where you had all those different, you had like a byte. You know, how big is a byte? It's an 8-bit signed value or signed int. And that can hold values negative 127 to positive 128, something like that. And then you had a short 16 bits signed int, negative 32,767 to 32,768. So on and so forth. Remember this guy? And I kind of mentioned, I said, okay, well, you know, what is an 8-bit or a 16-bit signed number? This is plus or minus 2 to the 7th power. because I said one of those bits is used for the sign. Kind of recall that how I advertised that? One bit is used for the sign. All right. Now, the question that surprisingly students never ask, because I do say plus or minus 2 to the 7th power for an 8-bit number, and this would be plus or minus 2 to the 15th power for a short, plus or minus 2 to the 31st power for an int, plus or minus 2 to the 63rd power for a long. But then I give you this range, and students never ask, well, why is the negative a different value than the positive? Right? Have you ever wondered that? Because really, when I say it's plus or minus 2 to the 7th power, that's not completely accurate. What's 2 to the 7th power?
128.
128. So plus or minus that would be negative 128 to positive 128. But that's not what it is. It's negative 127 to positive 128.
We need to include a 0 without the sign.
Okay, so somewhere in there there's a 0. We have 256 total values that could exist in there, right? That's our bit space gives us with 8 total bits. We have 256 unique numbers we can represent. All right, and if we want to keep track of negative numbers and want these to be signed values, then I've advertised that we're going to use one of those bits to hold the sign. Okay, which is it's mostly a truth. Okay, it's mostly a truth. With the maybe kind of the question mark that should have come up probably is, well, why is this number different than this number in terms of its actual magnitude?
Isn't that negative 128?
It is. It is. Thank you. And you'll actually see why that is here in a few minutes.
Does it have to do with negative 0?
It has a little bit to do with that. We'll see that here in a second. So we'll just call this old slide. All right, so we all kind of recall this slide from some point when we didn't ask that question about why the magnitude of the negative and the positive value are different. All right, so now we're going to talk about why they're different. So one of our ways of storing negative numbers. So put yourself in the shoes of the people who are inventing computers. They're like, okay, well, you know what? Positive numbers are pretty easy, or unsigned numbers are pretty easy. We have these bits that we're representing these guys in. We've decided we're working in binary. You know, biggest value, if we want to store in 8 bits, we can hold the value 0 to 255, right? No harm, no foul. 0 to 255, we're good. Okay. Now we're like, okay, well, we also want to represent negative numbers. So then we ask the question, how do we do that? How do we represent negative numbers? So now we have to start coming up with little schemes of how we might represent negative numbers. Okay, because this is ultimately a data representation issue. You know, we've decided that we represent characters, chars through like Unicode. Okay, and before that we used ASCII. Well, now we got to say, well, how are we going to represent negative numbers? So one of our approaches is something called sign and magnitude. All right, and this guy legitimately says, take the far left bit, and a 1 is a negative number, and a 0 is a positive number. Okay, that's what sign and magnitude says. All right, so we're going to initially show this in not with a byte. We're going to show it in much smaller chunks, if you will, so we don't have to do so much math. So let's look at a, should be able to do it in, yeah, we should be able to do it with just, let's do it with 3 bits. Actually, let's do it with 4 bits so we can look at nibbles. All right, so we have nibble, sign, and magnitude. So let's look at our values for nibbles. Nibbles are 4 bits. So a 4-bit number can be 0000, 0001, 0010, 0010, 0011, 0100, 0101, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0. You know what? Just for sanity's sake, we're going to do the 3 bits. We're going to say that's good enough. Okay, so those are, so we're just going to advertise this as 3-bit. 3-bit sign and magnitude. Okay, so we've decided we're going to use 3 bits here to represent our values. Actually, I'm going to keep it as a nibble. It'll make sense here in a second, the way I'm going to write this. So I'm going to do that. I'm going to steal this. Actually, I'm going to steal it here in a second. All right, so what is this value? This is a 0. This is a 1. This is a 2. This is a 3, 4, 5, 6, and 7. All right, so that's how we represent the numbers 0 through 7, the decimal value 0 through 7 in 3 bits. That's for unsigned. So now we're going to say, well, I want to represent those numbers, but I want to do it as 4-bit signed values. So I'm going to throw a 0 in front of all these. These are our positive numbers. Oops, sorry. All right, so those are our positive numbers. Now, I'm going to just copy this guy, put it over here. I'm going to change that leading 0 to a 1 for all of these. All right, so then these all become the negative versions of these. This is a -1, a -2, a negative 2, a -3, -4, -5, -6, -7. All right, so we look at this guy. Now, just for completion's sake, I'll go ahead and we'll throw negative in front of the 0 there. All right, now could we represent negative numbers this way? Could we use 4 bits to represent the numbers in the range of 2 to the 3rd power using sign and magnitude, where all the positive numbers have 0s in the far left and all the negative numbers have 1 in the far left? We could do that, right? So we can choose to just utilize the far left bit to hold the sign. What's the downside of this? What inefficiency exists with this guy? Go ahead.
Can't go higher than 7, or you're keep it 0.
Okay, so the can't go higher than 7, that really isn't the sign and magnitude thing. That's just the size that we picked, the 4-bit version of this. But the bigger issue here is that we have 2 representations of 0. So right off the bat, we can say that's inefficient. We only need to represent 0 once, right? You know, the Unicode character set doesn't have 4 or 5 different representations for a lowercase a. It has 1. 0 is a literal value, and we only need 1 way to map to that. Make sense? Okay, but this guy gives us 2 ways of mapping to it. Therefore, we actually represent 0 in 2 different ways. All 0s or a 1 followed by all 0s. Now, in the big scheme of things, is this the end of the world? Could this work? Could this be a way to represent negative numbers? Generally speaking, yes. There might be some other weaknesses, and we'll see that with like arithmetic later on. But generally speaking, this would fly. Okay, but weakness is more than one way of representing zero. So now let's look at ones complement. So in ones complement, we flip all of the bits. So zeros become ones, ones become zeros. We have to know that a value is stored in ones complement. It's probably fair to call this encoding, because we effectively encoded the value in ones complement. Okay, so we're only flipping those bits when we want to store the negative value. Okay, so I'm going to use this slide as a starting point here. So we'll do ones complement. Okay, so here's all our values, 0 through 7, positive. All right, so now what we're going to do, let me just cheat here. I'm going to copy this again. All right, so notice that every single one of these guys has a 0 in front of it. So before, we just changed the 0 to a 1. Now I'm going to flip all the bits. So now we have 1, 1, 1, 1, 1, 1, 1, 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 0, 1, 0, 0, 1, and 1, 0, 0, 0. All right, so again, this is our negative 0. This is our negative 1. This is our negative 2. This is our negative 3. Negative 4. Negative 5. Negative 6. Negative 7. All right, so this is our ones complement. So we've just flipped all the bits. Is this a reasonable way of representing positive and negative numbers? Is this better than sign and magnitude? It has the same weakness as sign and magnitude does, doesn't it? We still have the 2 representations of 0 when we don't need that, so we're losing a value. We could get one more value out of this rather than having to store 0 twice. So given that it has the same weakness as ones complement, really it's kind of worse than sign and magnitude, isn't it? Because if I have a negative number, if I give you this number and I say, oh, well, this number is in ones complement, before you can determine what that value is, you have to look at it and say, oh, well, it starts with a 1. So we'll just give this to you as an example. So let's assume that I gave you a quiz and you had the number 1100 in ones complement. So I have to tell you it's in ones complement. So at that point, you know that this number might be encoded. So before I go any further, when I say might be, notice that we didn't do anything special over here for the positive numbers, right? We didn't do any flipping of the bits or anything like that. We only messed with it if we were trying to encode it as a negative value. All right, so if I say this guy's in ones complement form, you're going to say, oh, okay, is it a positive number or a negative number? Negative number, how do you know? starts with a 1 over here. Therefore, what do you need to do? You need to flip all the bits. So this is actually 0, 0, 1, 1. And that is the value 3. And you know that it is a, we're going to do something like that. And since it was encoded in 1's complement, we're going to say it's a -3. That makes sense? So we had to decode it and then put the negative in front of it because we knew this was a negative number up there. Similarly, if I take like this number here, 0, 1, 0, 1, in 1's complement, okay, and I ask you what is the decimal equivalent of that guy, but I've given you the information that this guy is encoded using 1's complement. Right off the bat, you look at it, is this a positive number or a negative number? Positive number. How do you know? Starts with a 0. Okay, so since it's a positive number and it starts with a 0, do I need to flip the bits? Nope. So we just read the number. This is the 1's place, the 2's place, the 4's place. So this is the number 5, positive 5. Make sense? Okay, so 1's complement kind of makes some sense in a somewhat tricky way, but it doesn't really gain us anything over sign and magnitude. Certainly sign and magnitude, from just a human looking at it perspective, makes more sense. You got 4 bits, 3 of them are used for magnitude, 1 of them is used for the sign. I'll just read the 3-bit value as to whatever that value is. And then if there was a 1 before, it's negative. If it's a 0 before, it's positive. Pretty straightforward for a person, right? There are some mathy benefits of 1's complement, but not as much as there is for 2's complement, which is going to be the next one we're going to look at. Okay, so take the same thing here. So let's look at 2's complement. 2's complement says flip all the bits and then add 1. So it really says take the 1's complement, then add 1 to it. Okay? That's what 2's complement is. So let's look at how that plays out. So here's our 2's complement. Here's all of our positive values over here. Okay? Now for our negative values, I'm going to delete this. I'm going to steal this. So now we're going to flip all the bits here. So a 0, 0, 0, 0, 1's complement is 1, 1, 1, 1. But now I need to add 1 to that. All right, so let's pause here for a second and think about binary addition. 1, 1, 1, 1 plus, I'll just throw some zeros in here just for padding, plus a 1. Doesn't matter how many zeros we put in front of it, doesn't change the value of it, right? So this is 1, 1, 1, 1 plus 1. When we do our, well, let's, I'm going to pause this for a second and remind us of something we probably haven't done in years. Addition. Okay, so we had addition. When did you learn addition? Is that first grade? Okay, first grade. All right, so if I give you a number like 127, and we're going to add to that 1, well, let's just, yeah, we'll do 136. All right, now, if that was given to you today, you might try to do it in your head. Otherwise, you just use a calculator, right? Punch all those things in. But how does it actually work? We start at the right-hand side here, right?
Yeah.
And 7 plus 6 is what? 13. So what do I write down here at the bottom? 3. And we carry a 1 up here, right? Then what do? I say 2 plus 3 is 5 plus 1 is 6. Is there any carry off that one? Nope. And then 1 plus 1 is 2. So that's the number 263. So when I carried a 1, I carried 110, correct? That's what we had left over. All right, so the math we just did here is the same math we're going to do with binary. We take the exact same approach. So when I come in here, let's see, is it this one? So 1 plus 1 is 2. Is that one of our legal binary bits? Okay. Do you know what a binary, do you know what a base 10 number, what do we call one of these guys? What's like a 7 in a base 10 number? That's a digit, right? So what do we call this 1 or this 0 for base 2 numbers? It is a bit, but what would be the digit version of it for binary? And if you want to take a different route, we can also say the same thing about hexadecimal values or octal values. So this is a bidget, not to be mispronounced as a bigot. All right. And a couple of you have had 470 before. Remember the bidget assignment in there? That's a fun one. Huh? You erased that class from your mind. All right, so 1 plus 1 is 2, which does not fit. It's not a binary bidget. No, it's not a bit. All right, so we need to carry the 1. So this guy is going to be a 1 plus 1 is what with what carry? 0 with a 1 carry. 1 plus 1 is a 0 with a 1 carry. One plus 1 is a 0 with a 1 carry. One plus 1 is a 0 with a 1 carry. And that, I'm going to actually just bump all these over a little bit. All right, and then we technically have an extra 1. We have an overflow. Okay, because we're dealing with a nibble here, so we only have 4 little slots. Okay, so when I add 1 to 1, 1, 1, 1, I end up with 0, 0, 0, 0 with an overflow of 1. But the actual value I'm left with is 0, 0, 0, 0. Okay, so we come back up here. I flipped all the bits on this guy, right? So I changed 0, 0, 0, 0 to 1, 1, 1, 1, added 1 to it. I'm left with 0, 0, 0, 0.
I lost the game.
You lost the what?
I lost the game.
What game?
The game.
What's the game?
If you remember the game,
Mm-hmm.
if you remember the game, then
Yeah, just randomly. All right, so 2's complement. We flipped all the bits. We added 1 to it. 1, 1, 1, 1 plus 1 gives us a 0, 0, 0 with a carry on the front. When you read this value, what value are we left with there? We want to remember this one. Because when we come back here and we look at this was the area where we had our problem in the past, right? Okay, this was the area where we had our problem in the past. So right now we've put 0, 0, 0, 0 up there. Let that sit for a second. Flip all the bits here. 1, 1, 1, 0 is when we flip the bits. 1, 1, 1, 0. We add 1 to that, we're left with 1, 1, 1, 1. That's our representation. I'm actually not going to convert yet. You'll see why. All right. So then we're going to say, flip all the bits here. So this is 1, 1, 0, 1. 1, 1, 0, 1. We add 1 to that. So 1, 1, 0, 1 is going to be, this is going to become a 0. This is going to become a 1. So that's going to be 1, 1, 1, 0. Just show you what happened there. 1, 1, 0, 1 plus 1. 1 plus 1 is 0. Carry the 1. 1 plus 0 is 1. 1 plus 0 is 1. 1 plus 0 is 1. So that's going to give us 1, 1, 1, 0. Go ahead.
Right, so just to clarify, I mean, obviously what you're doing is like there's 1 and 1 in like the same
Place.
Yeah, same place.
Yeah, so 1 plus 1 gave us a 0 here underneath it with 1 as a carry above it.
Why 0? I get it because it's like binary.
Yeah, so we are borrowing the we're borrowing a 2.
Okay. So
Just like in decimal, we'd be borrowing a 10. We're borrowing a 2. 2 minus it'll make sense when I show you on this side of it. Right here we had a 7 plus a 6, which was a 13. We borrowed a 10, leaving us a 3. 13 minus 10 left us a 3.
Okay, and it's a 1 because in that place that's actually.
Right, so over here we had a 1 plus a 1, which was a 2. We borrowed the 2. 2 minus 2 gives us a 0. That makes sense because of what we borrowed. All right, so 1 plus 1 gave us a 0 as the result there. Well, it gave us a 2. We borrowed 2. 2 minus 2 gave us a 0, but we had a carry of 1, 2. Okay, 1 plus 0 is 1, no carry. 1 plus 0 is 1, no carry. 1 plus 0 is 1, no carry.
Could you still think of it as like 2 plus a 0 is 2 because like of the place it's in the binary?
Which one are you talking about here?
The second place.
So this guy?
Yeah.
Well, no, because we borrowed a single 2. When I say we borrowed 1, 2, we borrowed over in this one, we borrowed a single 10. We borrowed 1 10, a single 10. In this case, we borrowed a single 2 because we're doing base 2 math.
So when you're getting the answer, can't you kind of just think of it as like, okay, since it's in the second place and it's a 1, that's a 2 in binary.
It's all whenever you have a borrow up here, it's always going to be a 2.
Okay.
Yeah, always. I mean, the same thing's true in ours, right? If you are doing base 10 addition, you never have something more than a 2 up here. Because then it would have,
10?
huh?
You mean more than a 10?
I'm sorry, more than a 1 up there. Because you're borrowing the next 10 over to go. Yeah, so this one represents a single 10. This one represents a single 2. If we were doing octomath, the 1 would represent a single 8. If we were doing hexadecimal, it would represent a single 16. Okay, because when you, and the reason for that, the reason our math works in our decimal is this is the ones place, times 10 is the tens place, times 10 is the hundreds place. So when we don't have enough for our magnitude to fit in the place we're currently in, we carry a scale of 10 over to take us into the next group. Okay, and binary works identically. It's the same thing. We're just comfortable with base 10, and binary seems weird even though we're doing the same moves. All right. So we added it up. We're left with 1 1 1 0. So that's this guy right here. Next one are 3. Flip all the bits. That's 1100. Add 1 to it is 1101. This one, flip all the bits. This is 1011. Add 1 to it. 1100. This one, flip all the bits. 1010. Add 1 is 1011. Right here, flip all the bits. 1001, 1001. Add 1. I'm sorry. 100. My God. So this is flip all the bits. 1010. Add 1. This is 1001. Add 1 to that, we're left with 1010. Like that. Silver carry. So 1001, we add 1 to it. 1001, add 1. 1 plus 1 is 0, carry the 1. 1 plus 0 plus 0 is 1. 0 plus 0 is 0. 1 plus 0 is 1. 1010. Where am I at there? Was I on? I've gotten lost. That's right. 0. This is 1011. So I add 1 to that one, and I'm left with 1100.
So we're not like flipping it.
We're flipping it and then adding 1. We're flipping it first, which is 1's complement.
Yeah, but
then we're adding 1.
The way you're flipping it is not like just doing it backwards. You're just, if it's a 0, you're making it 1 instead.
Yeah, I'm just doing the math in my head. Yeah. So I just did this one. So the 0101 is 1010. Add 1 to it, it gets you that. 0110 flips to 1001, which will get you, when you add 1 to that, 1010.
That's the one I'm confused about. Because it's 0110 on the other side. So like you are.
Yeah, so we start off as 0110. That's what it starts off as.
So
then we do 1's complement. What's the 1's complement of that guy? Flip everything. Okay, so that's going to be 1001.
The way I was thinking of flipping it though is that it would have been the same thing, like 0110, kind of like race car backwards.
Oh no, yeah, no, you flip each bit. Yeah, you're not reversing it. Yeah, is that what you were thinking? We were reversing it. Yeah, we're not reversing the values. We're flipping every 0 becomes a 1, every 1 becomes a 0. Yeah, I get what you're saying. It's easy for me to, if I reverse that 0110 is the same thing backwards. When I say flip it, I'm talking about the individual bits. So this first 0 becomes a 1, the second 1 becomes a 0, the third 1 becomes a 0, the fourth 0 becomes a 1. Then you add 1 to it, and you're left with that. This last one, you have a 0 becomes a 1 becomes a 0, a 0, a 0, add 1, you get 1001. That make sense? Okay, so now, forget about these top 2 for a second here. Is there any other 0001 found anywhere in here? Any other 0010s? 0011s? Are all of these guys completely unique in the lists? Are all of these guys completely unique in the lists? One zero zero zero. We had 0 0 0 0. When we flipped all the bits, we're left with a bunch of 1s. We add 1 to that. Let's go back and do that math. 1 1 1 1 plus a 1 gave us a 0, 0, 0, 0 with an overflow. Make sense? We had a single overflow. Now, this is on the negative side of things. So that first bit has to be a 1 for negatives. Does that make sense? So at this point in time, do we have unique values for representing all of our different numbers? Could we actually say that this is a 0 to a 7 on the positive side? This is a 1 to a 7 over here. And this guy is actually an 8. Could we say that? Because now I have I have the ability to uniquely represent that many different values. So I've gained an extra unique representation that I did not have before. Now, what happens if I go to flip these? So let's say I gave you a 1, 0, 0, 1. 1, 0, 0, 1. I tell you this is in 2's complement. So right off the bat, you look at it and say, okay, the person's told me this is encoded in 2's complement, so I need to decode it. So the first thing we need to do is subtract 1 from it. Correct? To get us back into 1's complement form. So 1, 0, 0, 1, if we subtract 1 from that guy, what are we going to end up with? Well, right off the bat, this guy is this is the 1's place, the 2's place, the 4's place, the 8's place. But if this dude right here, this guy doesn't represent a number yet. This guy is a number representation. And I think that's the important thing when we're dealing with 2's complement. This is how we're choosing to encode a negative number. So whatever this number currently is, I need to subtract 1 from it. Whatever it currently is. All right. So how do I subtract 1 from a value in binary? Well, how do you subtract 1 in decimal? Well, you could cheat a little bit and convert these to decimal and then subtract 1 and then convert it back to binary, right? Otherwise, how do you do this? All right, so a 1 minus a 1 gives you a what? A 0 minus a 0? A 0 minus a 0? And a 1 minus a 0 is a 1. And let's look at it doing cheat conversion. This number here, this is the 1's place, 2's, 4's, 8's, so this is a 9. Is this the binary representation of an 8? Yep, so 9 minus 1 is 8. That's the binary 8. Okay, so we're able to do normal math. Then what do we do? We're in 1's complement now. What do I do next? Flip them again. Well, flip them for the first time here. So a 1 becomes a 0. 1, 1, 1. So this is a 1, a 2, a 4. So this is a 7. So that's a negative 7. So 1, 0, 0, 1 came out to a negative 7. 1, 0, 1, 0. What do you mean, is it a positive? It started with a 1. So since it had a 1 in front of it, we know it's a negative number encoded into. Well, the answer, this is a positive 7, and then we threw the negative in front of it because we had just decoded it. We knew it was a negative value because it started off with a 1 in the front. Yeah, so the negative we just popped on there because we knew this was an encoded value. We decoded it and threw the negative on the front. All right, so what was the value here? Just walk up. 1010. 1010 in 2's complement. All right, so I tell you this number is encoded in 2's complement. Right off the bat, you look at it, you see it starts with a 1, must be a negative number, therefore we need to decode it to find out what the number is. So 1010 minus 1. 0 minus 1 is a what? Well, what should we get here? We're subtracting 1 from this, right? So this is the 2's place, 4's 8, so this is a 10. So we should get a 9 out of this. Our final value should be 1001 once we're done with our math. So a 0 minus a 1 gives us a negative 1. What do we do with that?
We do like normal, like 10-digit subtraction. We pull from the value to the left.
Ah, so this guy would actually become a 0?
Yeah.
And then we get an extra 1. So we're borrowing from the other side, right?
Yeah.
Okay, so now 1 minus 1 is?
Well, it would be
You're borrowing after the fact.
Yeah.
So it's 1 minus 1, which is a negative 1.
Yeah.
We don't have enough juice. Yeah. So we borrow the 1 from the other side. So we have 1 and we have a negative 1, which gives us a 0. Mm-hmm. Right? Okay. 0 minus 0. Zero minus 0. 1 minus 0. Hold on a second. Oh, I did my borrow there. So this number here is a 10. We should have ended up with a 9. We ended up with an 8.
Yeah, it should have been a 1.
So we did bad math.
Yeah, that's what I was confused with.
1 0 1 0. 0 minus 1 is negative 1. Is negative 1 a legal bit? So you want to borrow from here. So you get a 2. A 2 plus a negative 1 gives you the 1. And we did borrow, so that became a 0. All the rest of the numbers become the same, right? Okay. So 1001 in 2's complement. This is a 9 currently. We've subtracted the 1, so we're technically in 1's complement right now, right? So then we flip the bits. 0 1 1 0. So this is the 1's place, the 2's place, the 4's place. So this is the number negative 6. Like we had here. Negative 5, negative 4, negative 3, negative 2, negative 1. So this guy up here, let's work backwards. Two's complement. Well, starts with a 1, so we know it must be a negative number. So we need to decode it. First thing we do is we subtract a 1. So 1 0 0 0 minus a 1. 0 minus 1 is negative 1. Can we borrow from here? So how do we do the borrow? Isn't it funny? It's been so long since we've done subtraction. Do we do subtraction in first grade too? That's a first grade thing?
This would just be 0, 1, 1, 1.
No, but I want to do the subtraction. Go ahead.
You do it by looking to the next spot and trying to pick from there.
Okay.
Spot to the left.
Okay, so I had nothing to borrow from here. So then you want me to go here? I have nothing to borrow from there. So I can go here. I have something to borrow. What am I borrowing? I'm borrowing 1, 2, a single 2. But where does that 2 go? Does it go all the way back here to the right?
No, it was one space.
One space over. So that was my 2? Well, actually, it didn't change that. It would have been a level above it, right? Let me do my carries here. So when I borrowed from this last guy, I made this. I borrowed a 1, which gave me an extra 1 here. Okay. Isn't that kind of funny? It's like, we don't know how to math.
You're borrowing 2 1s, and one of them is going over right away to the right.
Well, if I borrow, we got to think about the magnitude of this. If I'm borrowing from here, this is the 1s, this is the 2s, the 4s, the 8s. So when I borrow 1 from here, I'm borrowing not just 1, 2. I'm borrowing 1, 2 to the 3rd power. I'm borrowing extra. Now our cheat math works, right? You know, we can start off with this guy here and say, okay, well, this is the 1's place, the 2's place, the 4's place, the 8's place. So this is an 8. 8 minus 1 is 7. So what's the representation of 7? 0, 1, 1, 1. So that's what our answer should be that. Go ahead.
The way we write it is by writing 10 there. So it's sort of like you're borrowing 2 in the 3rd.
Okay. So instead of writing a 10, you'd borrow, you would put a 2 there for binary. Okay. And then this became a 0. Okay. Now we'll still write the 1 there. It was 1, 2 is what we borrowed. Okay. So now where are we borrowing from here? Do I still have another 1 I can borrow? So I get another 1 here. And then I get another 1 here. And now I'm able to do 1 minus 0 minus 1. How does that work? That doesn't give us a 1. Go ahead.
Well, those carries get downgraded to a 0, and so your 1, 0 in that spot becomes a 0, 1.
Which got downgraded?
So the first carry gets downgraded from 1, 0 into just 0, 1.
Yeah, so we had that. We represented that, right?
Right, and then the second carry does the same thing.
So this goes down to a -1?
No,
because we were left with we had a 1, 0, 0, 0.
Right. So if you think of like the top number as being part of the bottom number as well.
Yep.
You have in that column 1, 0. And so that 1, 0 then becomes a 0, 1 in order to throw the 1 to the next column.
So this guy becomes a 0, 1?
That becomes a 0, and then the one on the bottom becomes a 1.
Ah, so you want this to become a 1?
Mm-hmm.
And then when we borrow from this guy becomes a 1? And now we have this one left?
Mm-hmm.
But how do I make this turn into, because this guy becomes a 1. Now I have 3 1s?
The 1 that's left all the way on the right is really 1, 2 rather than 1, 1.
So this is a 1 in the 2's place. Is that what you're saying? Or is this, you're talking about a 2 up here? We're borrowing a single 2. So since we have a single 2, 1 minus 1, actually this is still a 0, right? 0 minus 1 is -1, plus the 2 gives us a 1. All right, so let's back up. Let's see all those things that changed as we remind ourselves how to do first grade math. All right, so we had a 0. We tried to subtract a 1 from it. We got a -1. That's not a thing, okay, in binary. So we have to try to borrow from our left. Nothing there. Try to borrow from the left there. Nothing there. Try to borrow from the left here. That worked. So in order to borrow this guy, he gets downgraded to a 0, and we're able to get our 1. Right? Now, that 1 became part of this number here. That's where that came from. Now we borrow again. We get another 1, which gets this guy to be a 1. Then we borrow again to finally get it over here. We get our extra 1, which is a single 2. 2 minus 0 minus a 1 is a 1. And then we just do the rest of the math. 1 minus 0 is 1. 1 minus 0 is 1. 0 minus 0 is 0. So we're left with 0, 1, 1, 1. So now we subtracted the 1 from this guy. What do we do next? So now I have this guy in 1's complement. If I need to get him in completely decoded mode, what do I have to do last? Flip 1, 0, 0, 0. It's the same value I originally had, but now we have decoded that value. This guy is a -8. This is the value 8. 1's place, 2's place, 4's place, 8's place. We knew it started off as a 1 here, so that means it's a negative number. We subtracted 1 from it, giving us 0, 1, 1, 1. Then we flipped the bits, getting us a 1, 0, 0, 0, which is the same value we started with, but this is the decoded version of that value. Does that make sense? Go ahead.
Would you give us one for this part of the test?
It's a 4-bit number?
Well, we could do 4, but would you give us
Well, probably not.
I don't understand how you could carry it more than 1 number 1.
If you want to cheat on a test, and even for our own sanity today,
It's an 8 minus 1.
yeah,
I got that.
yeah, you convert. Well, but isn't it funny how we've forgotten how to do subtraction?
No, I understand you do subtraction. It's like I don't understand how you could make the two middle numbers both 1s. Because if you're borrowing again, how can you not just make that the leftmost 1 is 0 if you're borrowing and giving the other?
Because you here, when you borrowed, this is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. So when we borrowed 1 from 2 to the 3, we're left with a single 2 to the 2 that we had here. Therefore, when we borrow again from that, we still have remnants. We have leftover. We didn't borrow all the 2's that were there. So when we borrowed a single 2 to the 3, we have a 2 to the 2 that we're working with there. When we borrow again, we just dwindle that down. It doesn't zero it out. That's where this 1 drops down, because it added to the magnitude of what we had there, because of how far over we had to go to get it. Every single time we borrow, we add 1 to everything that's on the way over. That's just how subtraction works, right? That's not how subtraction works?
Well, okay, so I'm thinking that if we're taking like 100 minus 99,
Mm-hmm.
You're gonna do it the old-fashioned way. You're gonna cross out the last 0 and you're gonna make it.
All right, so let's do this. 100 minus 99. I'll throw a 0 in front of it just so it matches what we're doing here. So 100 minus 99.
So you're gonna cross out the last 0 and you're gonna make that.
Oh,
Yeah, well, because you have to start on the other side. No. Okay. Can I do it?
You can do it on the board. Do we have markers?
There is a single marker over there. There's one
No, I'm not gonna do it.
We've gone very old fashioned here. I'll give us some spaces here to represent our so we can do what she's doing
We have
here.
100 and then we're subtracting 99.
Yeah.
And then if you're gonna want to change this to 10. But you have to borrow from this one, so I understand that. So you're gonna try to borrow from this, but you can't, so then you have to go here. So then this becomes a 0 and then this becomes a 9.
But it was a 10 that we borrowed from to get us the other 10.
Say that again.
When you got that 10, you couldn't give yourself that 10 until you were able to borrow from the left.
Right?
So that 10 became that 9 was a 10 until it became a 9 when you got the 10 over here.
Okay, so how do you change that with like a binary then? So then you're that's 11.
What?
The answer is 1.
Yeah. So what's the question you just asked? How do you change
Okay,
from binary?
so then in what we're doing on if you go to the left side.
Oh, well, this is the last one.
Well,
This one?
So we're trying to do 1, 0, 0, 1, right?
Sure.
Minus 1? Is that
Yep,
one?
minus 1.
Like that. So that's what we're trying to do.
Yep,
Yeah?
correct.
Okay.
And we know that with cheating, this should be a 8, right? So this is a 1. Yes,
Yeah.
this should give us an 8 is our final result.
Okay.
Okay.
Yeah. Is this one that we're trying to do? Or is
This one has an easier.
okay.
This one's gonna work easier. So
Okay, so we want this number minus the other number, right?
yeah, the 1 1 1 1, and then do the 1 1 1 1 1.
Minus 1.
Yeah, minus 1. Yep.
Isn't that still easy?
Well, 1 minus 1. Oh yeah, that one was.
Which one is the hard one?
1 0 0 0 minus 1.
Yeah.
Okay.
That one.
yeah.
Okay. So then you can't go here.
Correct.
So then we're gonna can't go here. So then we're gonna cross that out,
Okay.
and it's gonna be 0.
Yep.
So then what is this? Then we want this to be 1.
Well, what does that become in base 10 math?
What does what become?
If you were doing base 10 math and you
It'd
cross
be a
this out.
7?
No. Base 10. Base 10. You borrowed and it became a 10, right?
Yeah.
Okay. So if this was a base 10 number and you borrowed from here, this would become a 10.
This one.
Correct. So what is a base 2 number? What would it become in a base 2 number?
In that position?
The 2.
Okay.
So put a 2 there. Okay. So now you need to borrow again. So that 2 becomes a what?
A 1.
A 1. And then you were able to borrow, so now you got a 2 there.
This turns into a 2.
Yep. And now you're able to borrow from the 2.
So then that becomes that.
A 1. And now you have your 2 minus 1 is 1.
Okay.
Get it?
Yeah. That makes sense. Okay, so it's the 2. It turns into a 2.
Instead of a 10, because we're binary. If we were octal, it turned into an 8.
Okay.
So on and so forth.
I think part of the issue is that English is a base 10 language. So
Well,
we
no.
have trouble
This is why this is fun. The reason this is fun, and keep in mind I teach this every other year, so I get reminded of first or second grade math whenever we learn it. But it's always interesting, and what we'll do is we'll end up writing a program that does this, that reinforces it for us, right? But the idea is that we've been doing this for so long that we've forgotten how we do it. You don't think about subtraction anymore. right? You just pop it into the calculator and do it, or you just do it in your head like, oh, 10 minus 9 is 1. Who cares how we got to that? That's how we got, that's the answer, right? All right, so in any case, what we're left with here with 2's complement is we're left with an entire breakdown of all the values 0 to 7, and then on the negative side we have -1 to 7 to -7, and then we also have that extra value for -8. That's why it's bigger on the, well, smaller on the negative side. That's why we have the -128 to the +127. Does that make sense? We're getting the extra value because we don't have 2 zeros. Go ahead.
I think I'm confused about kind of what that's the problem. Like, I get what she just said, and I get what you're saying, but we ended up getting 1000 as our final answer, so it was still -8. So how was it if we did -8?
But it wasn't -8 at first. So even though it looked the same, so you're saying, well, if it originally,
You took the positive part. Like you took
no, not even that. So if I gave you, let's see, do we have it written down somewhere?
you
No.
read it on that last one.
I'm just going to delete this one and then I'll create another one here real quick. So if I say 1000 in 2's complement, right off the bat, you look at this leading one. You don't worry about what this value is. You just look at the leading one and say, ah, negative number. Since it's a negative number, it's encoded. Doesn't matter what that number is. It doesn't matter that we happen to end up with the same value. All we know is we have some digits that are currently encoded. Therefore, we need to decode them. Make sense? That's where we subtracted the 1. And when we subtracted the 1, we were left with, so we borrowed from here, which gave us a 2, borrowed from there, which gave us a 2, borrowed from here, which gave us the 2. So this left us with, I hate working backwards, so this left us with a 1 here. So our 2 became a 1 here, so that left us with a 1 here. Our 2 became a 1 here, so it left us with a 1 here. And then we had a 0 minus a 0, which is a 0. So that's the 1's complement version of that, right? Then we flip the bits. 1, 0, 0, 0. Now we're completely decoded. Now the magnitude of that value means something.
Okay,
So now we can look at it as an 8.
so it just happened that the value of it originally encoded was the same as it.
So the answer is yes, but that's also the magic of 2's complement. The whole reason that this one encodes and decodes to the same value is what makes 2's complement better than the other ones. Because those other ones, where are we at here for 2's complement? Because we get the extra value. If it didn't decode the same thing and instead it came out to, one of these other values, we've taken up every single other slot of 4-bit numbers. If it didn't decode to the exact same value here, then we would have been right back in that boat of having a -0 again. So yes, it did happen to turn into the same value, but that's why 2's complement is good. 2's complement lets us represent the entire range of positive and negative values within a certain bit space without having duplicates. Yeah.
Won't that happen every single time you subtract by 1? Because in changing it to 2's complements, you flip it and then add 1?
Yes, but all these guys are currently encoded.
Yeah.
So it will happen, but then you'll read the magnitude rather than decode it.
Right.
So the short answer is yes, but none of these guys will fully decode to the same value that was found over here.
Okay.
We know that these guys all represent negative numbers. Yeah, so the decoded version of it will be one of the numbers over here, except for the 0. The 0 is the outlier, right? So the decoded version will be what we would call a positive number, but because we had to decode it, it becomes a negative number. So then it's more to it than just the magnitude. Okay, so the magic of 2's complement is this stuff here. So what I'll do for next class, and hopefully this fills in some gaps from anything we talked about today. Go ahead and read section 2.4 from class. I might give you a quiz on Thursday, but if I give you a quiz, it'll be the difference between those 3 representations. I won't have you do math. We'll do math again on Thursday to reinforce what we did today, what you read about, then we'll do it again. Make sense? So a quiz won't have you do conversion, and a quiz will have you just tell me what's the difference between sign and magnitude, 1's complement, 2's complement. Got it? All right. I will see everybody on Thursday.